Good to go? Okay, can you hear me? All right, you want to turn the lights down? Okay, hello everyone. I am YJ Kim from National Weather Service AFS office. I'm the Chief of Analysis and Forecast branch, and listed here are co-authors who are our current and former branch staff and lantern participants from weather forecast offices. I'm going to talk about our effort to develop modeling requirements for global forecast systems based on users' needs identified from user feedback. And this will be part one about some background and introduction. So Analysis and Forecast branch, also known as AFS 11, in the Analyze, Forecast, and Support, or AFS office of the National Weather Service, has three primary tasks. First one is to collect and consolidate National Weather Service forecasters' needs for various analysis and forecast models and systems. And we do that through surveys, community forums, and other communication means. And we also develop requirements based on the collected information to address the field's needs. And we do that initially independent of developers, but in a later stage, we coordinate with them because we would like to make our requirements practically useful for the developers. And we also conduct some verification validation because we want to make sure that model and system capabilities are well aligned with the specified requirements we develop. So we are basically following this process to develop requirements, but we don't develop solutions, meaning models or systems. And this can be considered as a translation of field needs to requirements. Here are some key systems that we are targeting for requirement development. Three categories there are: observations, pre-processing, analysis and forecasting, and output post-processing. So far, we worked on MRMS and 2D version of Altimetroma, per HRF, and the NBM. And we are currently working on global forecast systems. And 2D version of Altimetroma, RFS, taking advantage of the requirements already developed for her and HRF. And indirectly on AWIPS, which is National Weather Service Data Dissemination System, because a lot of requirements we already developed for other systems include something related to AWIPS. I have a spare slide that I'm not going to show, but important fact that we keep in mind is that global systems affect regional systems, and regional analysis and forecast systems affect each other, and NBM takes input from a lot of systems listed here and others. So we keep that in mind to holistically connect our requirements to improve the overall performance of the systems. Some background for our global forecast system work. We first collected some sample field cases from the field that show some systematic deficiencies of the systems. Based on that, we developed a user survey and conducted the survey early this year to collect feedback from both NOAA and non-NOAA users, basically trying to reach out to the whole weather enterprise. Based on that, we analyzed the survey input as a preparation for developing draft requirements. I'm going to show some of them. And the survey data didn't include much information about S to S range, although we got a lot of information about short-term and extended range forecasting. And the needs we collect will be used for existing and future systems, including the SFS. So we want to reach out to more community, and notably, we get some good information from the CPC forecasters, which I'll go over later. So during and after this workshop, we hope to reach out to the whole weather enterprise to collect diverse needs for S2S applications. And this will be part one, and part two will cover some details of our case evaluation, survey data analysis, and draft requirements. And it will be a poster in conference break room A, and we'll share some details. And after my talk, my fellow AFS branch will talk about service aspects of the requirements from AFS office. I'd like to touch on some basics about requirements and our office's role. We had NWS Governance version 4 that defines the requirement and the role of our office, AFS office, basically to identify, validate, prioritize field needs, and develop requirements. This year, there is a new version of governance that came out, but it's only a draft without many details, without new definition of requirement, and it's pending further revision and approval. So we are kind of in a transition phase until the new governance is finalized. So we are kind of operating based on both governances. And I just wanted to check if we are doing okay and was interested in how others are doing. So I asked ChatGPT this question: how should the requirements for weather forecast systems be developed? So it gave me an answer as expected, but it showed me 10 steps to follow. And it was good to confirm that actually FS11 is taking a lot of steps listed here, like stakeholder identification and engagement, and gathering and analyzing requirements, needs, and developing requirements and doing some follow-up. And also, there is a high-level council called Mission Delivery Council under the old governance, and Mission and Systems Integration Council under the new governance. And that council is doing a lot of work, like reviewing and validating requirements and prioritizing them. So I think we are doing okay. And step 2, regarding the definition of scope and objectives, we feel that there is a gap because it's not very clear how to define the scope and objectives for modeling requirement development and also modeling development itself. So we're going to work on this high-level policy or directive to fill the gap. And I want to touch on priorities. There are different priorities. Forecasting priorities set by forecasters, in our case, NWS field. And development priorities set by Modeling Program Office, in this case, STI. Modeling priorities set by model developers, in our case, the EMC. And there are different kinds of priorities set by Forecast Policy Setting Office, which is AFS, implementing various needs. And when it comes to modeling requirements, is my branch that is taking care of the work. And it's only after these priorities are consolidated by AFS11 and validated by the NWS governance process, we can call them requirements. So there is clear definition about requirements. In theory, requirements should be available before models are developed, but unfortunately, FS11 was established relatively recently when all the models are already existing. So we are trying to catch up and trying to provide a best set of requirements to meet the needs of the NWS forecasters. And what's happening here is all the parties, forecasters, developers, and program managers are involved in setting these priorities one way or another. But I'd like to note that FS11 is initial and final authority for modeling requirement development. And there is something called CART, Capabilities and Requirements Decision Support process, according to the previous governance. But although there is a new process tentatively called NWS requirements process, according to the new governance, the CART will remain the primary tool, although it may go through some revision. Some examples of needs, stakeholders, requirements, and solutions for S2S. The needs include seasonal outlooks, extreme forecasts, reanalysis and reforecast. And there are different stakeholders: NWS field, public sector, private sector, and other, including academia and UFS community. And what we are developing in terms of requirements are for NWS field. We are not aiming at meeting all the needs of all the stakeholder groups here, only NWS field. But we believe that our requirements will be useful for other stakeholders as well. So that's our assumption. And in terms of solutions, it can be systems or some performance metrics, such as those for teleconnection indices. And here I'd like to note that whether the systems, the models are developed by the community or NOAA, as long as they are used for NWS forecasting, those systems should meet the requirements for NWS field. On the other hand, the needs can be obtained from the whole weather enterprise because they will be useful, and that's what we are doing. We conducted a survey this year, and that is for all the weather enterprise community. And it's formally closed, but it's not too late. You can participate if you have any needs or thoughts you want to share, and you don't need to answer all the questions, only those you want to answer. So after the validation, we plan to share the requirements with the whole community. Finally, we are talking about some requirements for global forecast systems. And please note that this is not a complete list. It's based on our initial analysis of the survey data, roughly in two categories. First group on qualities and quantities, and second one about threshold and timeframes. We have some general requirements about TCs, winter storms, and some basic parameters. Notably, we have TC genesis, false alarms, and right of track bias issues. And there are some specific to CFS and SFS regarding warm bias, model upgrade, resolution enhancement, dispersion increase, and unanswered period extension. And there are others talking about related to boundary layer mixing, core layer damming, QPF, gap spread, and the well-known progressiveness of for large-scale troughs and track performance matching. And the other category is about threshold and timeframes. And I'm not showing any values here, but you will find those values on the poster this afternoon, so please visit the poster. And we have another category about data availability and access on AWIPS, our data submission system, because no matter how good these products are, if they cannot be delivered to the desk of forecasters in time with sufficient amount, it's no good. So we have a special category touching on those requirements. And here are some direct requirements for SFS. And I'd like to thank Corey Baggett and his team from CPC's Operational Prediction Branch, who provide us with a comprehensive set of needs for CPC forecasters. We are in the middle of digesting them. But here I just show one example. They want full read forecast data set whenever a model is upgraded or reconfigured, ideally matching real-time configuration in terms of initialization details, ensemble size, and well in advance prior to real-time forecast implementation. So again, please have a conversation at the poster. So I don't think I need to read these through, but just want to note that I understand the organizers of this workshop is planning to send out a survey for SFS system needs, and let's coordinate because we are very interested, and eventually those will have to be processed as requirements if that's for NWS application. Again, that's strictly restricted to a NOAA domain, but I want to take advantage of this talk to mention that. And here are down there details of the part 2 poster and the next talk, which will be about service requirements. So I don't know how I did in time, but that's all. Thank you.
Thank you, Young-Joon. We're going to save questions for the end just to keep things moving. That's okay. Excellent. Thank you, Young-Joon. For time, we're going to keep going and we'll do questions at the very end. Our next speaker is Marina Timofeyeva. And I apologize if I butchered your last name.
Me? Share. Come on. Stop. Window. It's not giving me the option. Okay.
How to see the buttons?
You can just use the mouse.
Okay.
Or you can just click through.
Okay. Okay. Hello, everyone. Wow, it's so dark. YJ made an excellent introduction to my talk. Thank you. I will be talking about service requirements and specifically how to connect weather service and NOAA's goal for building a climate-ready nation. And first, I would like to acknowledge my co-authors. It definitely takes a village to put this all together. And this is mainly climate services branch, but some field people who were helping us. Field people, I'm talking about WFO, Weather Forecast Offices and Weather Service. In the talk, I will be talking about how we are collecting the user needs. And we have different engagement avenues. We are engaging our field officers who are in front line with working with our users. We are talking with external professionals who are working in extension sometimes or making a research on climate applications. We also conduct customer satisfaction surveys. When we are collecting the requirements, we are definitely putting this all together in the annual operating plan. And the roadmap that we developed for 2025-27 is summarizing mainly what are the needs and how we can advance our services. And this definitely has a ties to Kent State, Weather Service Strategic Plan, and Climate Ready Nation initiatives. Oops, it doesn't go further. Okay. So I will start with weather service field engagement. In 2023, we had a very extensive field engagement, including surveys, focus group, national meeting, workshops, and what we came up is this statement of needs for S2S services. Of course, people need informational resources for climate services delivery and attribution of the studies. They need to have improvements in products and tools, forecasting tools development. And they need specifically tailoring the information to their core partners' thresholds. They need to have IDSS, IDSS, probabilistic IDSS, baseline services, you know, what does it mean? And they need to have more clearly connection between national scale products, maps, and local scale. What does it mean to translate it for local level? There is a lot of things already have been done in this direction, but we need kind of like a clauses that it would be much easily connected. And capacity development, outreach materials, training, service tools that it would be easily and handy information. We need to have partnership and communication practices and talking points and other graphics materials and everything else. Through engaging with professionals, we're using our annual climate prediction application science workshop. And on the example of heat that will be shown here, I will show to you that we are working on gathering requirements. And for example, for heat and drought risk, people need information that would be summarizing both cascading impacts of extreme temperature and precipitation deficiency and service delivery practices. Moisture deficit needed for recovery from drought and not only drought state. Identifying user needs, formats, and people like we are using surveys, focus groups, one-on-one decision support, training sessions, and discovering the information like this. And definitely CPAS helps us to showcase applications and tools that I will not be talking here about. For the heat session presenter, we had a poll. As a result of this poll, we discovered what are the user engagement practices that I talk about, how to address service equity, consistency of the products at national and regional and local level, what are the good performance metrics, what are the people are using for measuring successes. And S2S and climate change services that I will be talking in this presentation specifically. And this is what outcomes from this survey. Of course, people need to have more advanced scientific knowledge of S2S impacts, not only the information what would be, but what would be cascading and compound impacts of the services. And ways for improved products, we need longer time leads of the outlooks, and this was coming again and again from different presenters. Skill information available, better mapping capabilities, more intuitive, decision-ready information and data. And for subseasonal and seasonal decadal trends are equally critical. What people are making information decisions on subseasonal scales impact the climate change information, how they're approaching, and vice versa. And definitely there is a lot of inconsistency in climate projections, and people don't really know what to use for their needs. When we talk about in 2023, we conducted specifically a customer satisfaction survey in weather surveys that were focusing climate prediction center products. And this is the outcomes of the results that I'm showing here. So in general, to measure scores, they're using American customer satisfaction surveys. It's kind of like a standard survey that are taking satisfaction and some economic benefits of the products. And they say that, you know, our scores are not so bad, but, you know, when I'm looking at comparison of the scores that were like 2004 and 2009, they are a little bit lower now. Our users need to have more intuitive information, more easy understandable information. What was good in 2004, 2009 could be improved now. In the survey results, we identify user cases. Social, behavioral, and economical sciences speak to us that you are asking wrong questions from our customers. Instead of what do you need to say, what do you do with information? And we try to address these exact questions. And we know that there is in transportation, radioactive waste decisions, financial decisions, ranch and mountaineering planning and safety decisions, water management, there's contributions to US Drought Monitor, it is help, community help to improve the products. US citizens use different information, and agriculture. And when we look at this is a summary of suggestions for improvement. People definitely need hyper-local climate observations and forecasts. They need to have down to the ground where the decisions are made, because some information is not have sufficient resolution for their decisions. Definitely, expectations are for more organized, modernized, and user-friendly information with better navigation system and climate maps. Easily defined terms of information like below, near, and about normal is not easily understandable, and you need to have access to historical weather data, and to have access to drought and climate maps on regional and local websites. So no matter where you will come in the weather service, it would be no wrong door for users. YGA talk about cards. It is capability and requirements data support, and there is several projects now in the pipeline to identify whether these projects particularly are within weather service mission and how to resource this project. And one of them is requesting this, the last one, coastal flooding outlooks, is now in the is a project for social, behavioral, and economical sciences to see what are the needs and how to identify what are the capabilities and gaps for 4 to 7 days and subseasonal to seasonal coastal flood outlooks. And there is coming local climate analysis tool that is a tool not for forecasting, but for using the information, the adding value to the forecast. For example, when the service is calling for equal chances, what does it mean for users? What can we say? And we can say something more to this. I promised to talk about roadmap. So all these requirements from different sources of information were assembled together and look at this strategically how to move forward with this. And we identify 4 major themes here. This is climate observation, monitoring and predictions, collaborated climate messaging and decision support, application of weather service areas and societal needs, challenges, and incorporating multi-scale climate information to products and services. This is major themes that will help us to advance our future weather service climate services. And what takeaway message I want you to take here is that there is a lot of S2S information in the pipeline here. Essentially, it is everywhere, but we needed to start somewhere, and I highlighted here 3 major things that we took in fiscal year 25 milestones in our annual operating plan. This improved services for compounding and cascading hazards, climate services IDSS concept of operations document. And in the gray box here, weather service is talking about new operating model, because operations models that we developed, we are using now, was developed 40 years ago, and there is definitely need for change. And now we're all working to see what are the good options here. And if definitely one of this is addressing service equity and for US affiliated territories and Hawaii. When we talk about new operation models, you see what we have now is the top part of this, is we have a lot of on the national scale and very few capabilities at local scale, and we would like to switch this information. And this definitely would be climate IDSS for drought, coastal heat, flood, wildfire events, climatological risk of extreme and water events, value added to NWS core products, placing service requirements, and so on. There is a definitely strong connection to climate content, specifically in the weather.gov new operation model, AWIPS in the cloud, probabilistic IDSS, and the day 4 to 7 at NCEP. And definitely the climate ready nation, because we are driving to multi-scale information that would be available here. And I would like to end my talk with the reflection of 2023, because we celebrated regional and local climate services and weather service in 2023, and we reflected what was good done and what was the history, what are the building blocks we have now in the program, and what are the lessons learned. And specifically, I wanted to talk about climate availability, science availability versus user needs. We definitely need to merge these two closely together. Partnership for co-development and co-production and service cutting. The climate is a service cross-cutting for all programs. IDSS between weather ready nation and climate ready nation, and infusion of social behavioral and economical sciences in the operational product suite. Thank you very much. I know that I don't have any time for questions, right? Thank you.
Marina, thank you so much. I'll be reaching out to you for some questions here in the next few weeks. I learned a lot there. All right, we are going now to our next presenter. Our next presenter is Royce Fontenot. Hope I said his name right. And Royce is coming to us remotely. So I will. Royce, can you hear us?
Yeah, can you hear me okay?
Yes, we can. Floor is yours.
All right. Good morning, everyone. I'm Royce Fontenot. I'm one of the senior hydrologists down here at the National Weather Service's National Water Center, and I'm in the Operations Division in Tuscaloosa, Alabama, where I am this morning. I'm also the Water Resources Program Lead here at the National Water Center. So my discussion today, we've had some great lead-in discussions. It's going to be taking not from a technical perspective, but taking it from the perspective as an operational hydrologist, as someone who's out here on the line, creating and developing these forecast products. So I want talk a little bit about what our requirements are for the next generation of medium and S2S models. From that perspective, we're going to have some great talks. Some of my OWP colleagues are going to be speaking this week, some of other water focused talks, but how will give you an idea of what we're thinking about from the operational side. So let me quickly introduce ourselves as the Office of Water Prediction, which is where the National Water Center lives, and some of our vision and mission requirements. So for those not familiar, Office of Water Prediction is the functional equivalent to NCEP, National Centers for Environmental Prediction. We're on that same level. And the National Water Center is the functional equivalent to the other national centers such as CPC or WPC. In short, our vision is a water-ready nation that can address the challenges and the facets of all everything to do with water, from flooding to drought. Our mission succinctly is to provide the operational hydrologic intelligence to water customers and decision makers. That's ranging from the emergency manager concerned about flooding in the next few hours to the farmer in Iowa looking ahead to next year's planning. So we cover that whole spectrum. We're also one of two only national centers, us and CPC, that covers everything that the National Weather Service covers. So we have responsibility from our colleagues out in the Western Pacific and Southern Pacific Ocean all the way over to Puerto Rico. So let's talk about the priorities for water stakeholders. And this is really a time span. They really need an integrated understanding of water in the short term. It's usually flooding, right? Next few hours, what's going to happen, next few days, weeks. For the longer term, which we generally think about water availability, but in reality, it's an outlook for the complete hydrologic environment. And where that's key for us here at the National Water Center and Congress's Authorization Act, they declared that the Office of Water Prediction National Water Center is responsible for total water prediction. That is going to be the entire hydrologic cycle. We're including things like coastal inundation mapping, inland inundation mapping, water supply, the whole gamut. So our stakeholders are looking for this whole spectrum, but they ultimately need actionable intelligence, often down to the street level. But in the longer term, they're wanting to know not just what the flood risk is, but also water quality, water availability, that whole hydrologic cycle. So the key to this is everything we do, I had previously mentioned this, needs to be actionable. So let's talk about some of our challenges as forecasters here in the medium to S2S timeframe. So one thing to really think about is water is both a resource and a hazard. So remember, the mission, as previously stated, the National Weather Service is protecting life and property. But if you look at our mission statement, it also includes furthering the economy of the United States. So that's really the resource part. One reason we're in the Department of Commerce, right? So that's kind of where this comes in. It's both a resource and a hazard. We care about flooding, obviously, but we also need to know if we're going to have water. Even in an extended time frame, the flood part matters. So does the water availability. So in this space, the user needs are going to be different, and that's a challenge. What the U.S. Army Corps of Engineers needs to plan for potential flood fights in 6 months in the Midwest is different than what the barge community on the Mississippi and Missouri River is going to need, or the hydropower generation in the Pacific Northwest, or even in Arkansas where you have hydropower generation. The other catch is, as it's brought up, we need to be probabilistic in our outlooks. So hydrology, operational hydrology, we've been doing that for a long time. We were some of the early adapters with water supply of probabilistic forecasts. However, for a lot of users still need a number for their planning and their trigger point. So you have this dichotomy that, I want this great probabilistic spread of information, but they need sometimes just a number, and including us hydrologists, and I'll talk about that. Precip events are often too short to be adequately captured in the medium to S2S. So that's obviously going to be the flood part of it, or even breaking a drought. And those are what drives our extremes. And let's be honest, the models, precipitation forecasting is probably the thing we're weakest at. It's not that good that far out. But we can get really good trends, and trends are useful. But again, how do we get those trends to a number and a value we can use, and I'll talk about that. Currently, our operational medium to seasonal range hydrologic outputs are really point-based and mainly focused at specific river forecast point that's calibrated by the 13 river forecast centers. It's typically a river gauge. So the catch is, while this is information that's tried, it's true, it provides actionable DSS, it doesn't account for areas not represented by the model. Things that are off, not at that river forecast point. Things that, aren't on the channel at all. There's industries that need to know what the cycle is going to be. So these are some of the big challenges we have as we're developing these products and we're looking ahead and the path we're going to go. So let's talk about currently what we have out there, and then conceptually where we want to go with forecasters, particularly the S2S range. So let's talk about GEFS and the current water supply forecast. This is two examples. On the left is just a generic graphic from GEFS, which is the Hydrologic Ensemble Forecast System. And we're going to have a talk later this week with one of my OWP colleagues, specifically talking about some of the requirements there. And on the right is a graphic from the National Weather Service's water supply forecast. This is particular ones from the Colorado Basin RFC. Not shown here is the multi-model ensemble forecast system, which MEMFS, which is run by some of the Eastern region, or the long-range outlooks that we use in producing the National Hydrologic Assessment, also known as the Spring Flood Outlook. That's not included here. But so here's some key points. These report forecast specific locations. On the left is stage and flow. On the right is seasonal volumetric forecast, which is often what they're looking at. Water supply in the west are looking at volume versus actual stages. These are both great tools for those users at those specific forecast locations. Just some hand waving information about GEFS. It can be run in multiple configurations, and it is. Each RFC has a little bit different flavor. Most of them go out to about 16 days. There's a long range configuration out to about 28. A few RFCs are using the CFS to go out to 270 days. That's not very publicly available, but we're watching that. So here's something to think about as we're developing. And this is kind of the things that we have a lot of developers and the technical folks. I want things to be thought about, is both of these are using 6-hourly data in hydromet forcings, and they're using the RFC model. Keep that in mind. 6-hourly data, forecast data, out to 16 days, out to 270 days. Both these are also statistical ensembles versus the MEMFS. So the ensemble forcings generated on the hydrologic model side, it used, for example, the GEFS uses the GEFS mean, and there's some reforecast information. Again, there's going to be some further discussion of that. And then water supply forecast is using climatologies after a certain point. So they're great tools, but they're point-based. So if I'm not at a calibrated river forecast point and I need that information, I don't have that. So the next tool we have, and this is certainly something that's probably been one of the biggest things that we're working on here in OWP, is the National Water Model. So right now, the beautiful thing is it's not just at points. The National Water Model here in the continental United States covers 3.4 million river miles. That's compared to about 3,400 river forecast points, give or take. And we're also now producing services in Hawaii, debuting some internally some additional services in Alaska this week, mainly in South Central Alaska and Puerto Rico. So we're running this constantly. So I also want you to pay attention to those numbers on the left side for the model developers. We're running 3 configurations of short range, which for the CONUS goes out to 18 hours. We're using hourly data. For the medium range, right now, it's the GFS and the MBM mean. It's the operational GFS. Note, we're not using the GEFS at this point, but that's probably coming with our next gen. Those are 1 hourly forecast. And then we're running the CFS as we're talking about how often we need this data. And there was a discussion earlier today. We're running the long range configuration of the water model 4 times a day using all 4 outputs of the CFS. And then we do a mean as well. Right now it's a 30-day ensemble forecast. So the 4 ensemble runs plus the mean. Right now, not planning on a 270-day run. That might be something we look at down the road. But a key to keep in mind is that we need the high resolution. And because the type of model it is, we need that high temporal and spatial resolution data. So here's a current example. Our focus has really been on the short and medium range forecast. We're still developing a lot of the tools for the long range forecast visualizations. But here's currently what we have. This is an example. This is a CFS forced national water model run, stream flow anomaly. You can get the full output on Nomads if you're interested in NetCDF, but this is what we're doing. And right now it's channel based, which is great. And this shows trends. So I'm getting those off forecast point areas, but as showing trend, I can use trend. But one thing we're not really doing, and we can get from the model, is how's this going to visualize for those areas that need something that's not on the channel? They need that area that's the national forest, that they need a general water balance. They need something better in the long run. One thing to note, and one of the lead authors on this, or the lead author, is going to talk later this week, but the current long-range forecast, in hindsight, in retrospective mode at least, does show some skill in predicting drought. There are concerns with the current forcings, the CFS, and there's concerns some of the particulars of the model may limit operational use. We haven't started using it yet. But like the saying goes amongst operational forecasters, all models are wrong, some are useful. So there may be usable signal and trends and such as we go along and develop it. So we're looking forward to evaluating that forecast configuration. But this is what we have now. And this is that in between of what we're looking at and what we're going to, what we have now. So we have the really good calibrated models at forecast points. Now we have a model that's going to provide hopefully some scale at the 3.4 million river locations. But what about those areas? For example, if you look over Western Texas, Southeast New Mexico, there's not a lot of channels there. What about those areas? What about those areas that don't have that same information? So that gets us as an S2S. And to me, as a operational forecaster, I consider myself a climate geek. This is, to me, the biggest challenge moving forward, is that S2S workspace. So what I want to talk about on this slide is, on the left, we've got the CPC seasonal outlooks, which give that, above, below normal values at equal chances. I've been using those since I was an undergraduate 30 years ago almost. They're great for broad signals and usage, but we need numbers. As the kind of top bullet says, that as an operational hydrologist, an above and below normal, I can't use that in a model. I need a value. Now, it can be a range of probabilistic values, but I need an individual value to put in there, that water balance sort of equation on the top right. And I'm going to start hurrying up here. So, how do we translate these forecasts into the usable product we need there on the right part of the slide? How do we take that CPC 3-month forecast that does have POE values, but I've got to deaggregate that. I've got to get it gridded. I need a higher resolution. So this is one of our things that we're looking for, and something to think about for the developers going out as the forecaster. We need some good spatial resolution. We need temporal resolution. You saw some of our models need hourly. Some of them need 6 hourly. And the other thing is we're looking at that entire, and the two previous two previous presentations talked about this. We're looking at everything in that blue box. So the users are multifaceted. They're not just looking at what runoff is at a particular stream. They're looking at evapotranspiration. They look at groundwater. They're looking at that whole suite. Remember, we were given the mission of total water prediction, and the user base also will include forestry management, forest fire management, the barge community. So there's this wide range of users. So how do we get from the NMME on the left to something we can use to input into that water balance model to give you things on the right? And the other challenge there is we've got to get it probabilistic. And we need forcing values in acceptable scale and temporal scale. So I summed it up: challenges and needs. So water is a resource and a hazard. So we've got to deal with both sides of the coin, and users need different sides of the coin. So I put up 2 challenges and 2 needs. First, our challenge is that we need numbers. For hydrologic modeling, the above and below, we can't use it. We need an actual number. Now, we can use a suite of numbers, but we need an actual number. That's the real challenge, right? Especially when I'm listening to you, the modeling community, talk about runtime and where do we need to put this in computing resources. Challenge number 2, we've got to provide that range of forecast solutions to a wide range of users. We're not focused on one particular user. That user may also have multiple ranges of concerns. And so it goes everything from point-based to off-channel to a small channel not modeled. And they need that in a variety of timescales, days, weeks, and months. Are we looking at flash drought, which may affect things in the next 2 to 3 weeks? Or are we looking at next season when you may be planning your planting or your barge availability or other things? So I guess my overarching thought is, as you're going through, keep us in mind on the hydrologic side that we're going to need things in different temporal resolutions and different spatial resolutions. We just had the previous talk about too high resolution. That's certainly possible, but not too gridded, not too large, because then we may miss on the signals. So that's what I got. I'm right at my time, and I appreciate everyone taking this.
Royce, thank you so much. That was a very interesting discussion. All right, everyone. Our next speaker is Hailan Wang.
Hello, everyone. I'm Hailan Wang from NOAA Climate Prediction Center, also called CPC. Next, I'm just going to switch gear a little bit to talk about drought prediction, mainly from the point of view of a drought product developer perspective, and hopefully can serve as a nice complement to the previous presentations, which had a strong flavor of service and also hydrological forecast. So specifically in this presentation, I'm just going to talk about the probabilistic subseasonal-to-seasonal forecast of US drought, talk about the challenges and needs we experience at CBC when we develop our probabilistic S2S drought outlook products. And in this presentation, just for convenience, I'm just going to use this context of our ongoing work, as I just mentioned. And here I'd like to acknowledge my co-authors, as listed here at CBC, who all made substantial contribution to this effort, this product development. And also like to acknowledge the funding support from few programs. In particular, appreciate very much the funding support from NIDIS for this work. So first of all, just in case some of you are not entirely familiar with drought, so what is drought? Just according to MS glossary, drought is referred to a period of abnormally dry weather that is adequately long to cause a shortage of water. But getting down to the specifics, the picture described by drought is more complex than it sounds. So drought typically would be initiated by what happens in the atmosphere, such as precipitation deficit or heat waves, referred to as meteorological drought. And these meteorological anomalies can subsequently lead to the dryness at the land surface, such as the dry soil, vegetation stress, and reduction in crop yield, referred to as agricultural drought. And on a longer time scale, we can also have hydrological drought, just typically manifested in the deficit in surface water and groundwater. And all these drought types, meteorological, agricultural, and hydrological drought, they can lead to socio-economical drought because they can exert this adverse impact on the society, economy, and environment. So just in short, drought is a multifaceted and multivariate phenomena with cascading impact. And really, there's no single variable or single index with a fixed time scale that can be adequate to describe drought as a whole. So the question is, at CBC, how do we forecast drought? At CBC, we recognize drought as a multifaceted and multivariate phenomenon, and we forecast drought as such. And as I just mentioned earlier in this presentation, I'm just going to use this context of our ongoing development of CBC probabilistic drought outlooks. But I also want to mention that the challenges and needs that we experience at CBC is in general applicable to the S2S drought forecast in general. So here's the framework we use. We will start from subseasonal and seasonal dynamic model forecast, which typically would produce the forecast for meteorological forecast for precipitation, temperature, and other variables. And then we would apply post-processing, including bias correction and calibration, to improve the skill and reliability of the meteorological forecast. And also, whenever feasible and available, we would like to incorporate statistical prediction tools to further increase the skill of these meteorological forecasts, especially the forecast for precipitation. And then we would use these meteorological forecasts as an input to drive land surface models of land to produce a forecast for a basic set of land surface variables such as soil moisture, evapotranspiration, and others.
And then from these two steps, we'll be able to get the forecast for the list of atmospheric and land surface variables, which would allow us to produce a forecast for a variety of drought indices describing different drought types and different timescales. And subsequently, we would develop objective drought blends to objectively blend the forecast for different drought indices of different timescales to produce a forecast for integrated drought conditions, including those for short-term drought, long-term drought, flash drought, and all drought conditions. And lastly, for the product development, we need to incorporate social science to finalize our product visualization and dissemination. So just within this framework, if we want to produce a skillful and actionable drought forecast product, then we will need to have these requirements. We will need to have skillful forecasts of precipitation temperature anomalies, because these are the key meteorological anomalies that drive drought evolution. We also need to have the skillful forecast of the land surface variables. And for the generation of forecasts of different drought indices, we need to have available to us a forecast for a list of atmospheric and land surface variables that are needed for calculating these drought indices. And for the next step, we need to have these objective drought blends that apply to forecast, not to monitoring, that need to take into consideration about the different physical nature of different drought indices. At the same time, also need to take into consideration their varying forecast scale, so that the integrated drought condition that we're going to produce forecast for can be skillful. And for the product visualization, dissemination, we need to incorporate social science. And lastly, always need to involve this active user engagement so we can better understand their specific needs in order to make connection to our product to better address their needs. So next, I'm just going to talk about the challenges associated with each of these items. The challenge number one will be associated with this limited forecast scale for precipitation and surface air temperature for subseasonal lead time, which is really well known to everyone. And here is about this schematic diagram. And now we know that the reason that we have this limited forecast scale for subseasonal and seasonal lead time is mainly because that we have this limited sources of S2S climate variability. And on top of that, our current forecast systems, including our physical climate dynamical forecast system, have a variety of model biases, which to some extent can prohibit them from properly leveraging all the known sources of S2S climate variability. And as also mentioned earlier, why we care about this for drought prediction, because precipitation temperature anomaly, they serve as a key driver to drive the change of drought condition with time. And in fact, this effect of a limited forecast scale for precipitation and surface air temperature is pretty well reflected in the CDC drought product that we produce. Here, just use the CDC seasonal drought outlook as one example. As you can see, this is our operation product issued on a monthly basis and provide the drought forecast information for the upcoming 3 months or so. And in case some of you are not familiar with it, so here's just sample plot. So basically the visualization just use the format of a national map color-coded to show the drought tendency category, whether they're going to improve or remains by improve or remove likely or persist or development likely. So as you can see, we have a large number of seasonal drought outlook as we have been working on this for almost 2 decades. So using this, we can build the statistics, and here is what our CDC drought forecaster produced on this skill assessment. And here just want to bring to your attention this skill dependence on drought phase, especially for this one. So what is shown here is a skill for the drought development, which refers to the condition that we evolve from no drought to drought, which are typically forced or driven by meteorological anomalies such as precipitation deficit and heat waves. And because the current forecast system have a limited forecast scale for precipitation deficit and heat waves, and so it just kind of in our product development just kind of translate into this limited forecast scale for drought development. And even though not shown here, for the subseasonal drought forecast, we can see similar indication, similar low scale in the forecast for subseasonal drought development, such as flash drought. And second challenge will be in the area of land surface forecast. If we think about the factors that would influence the forecast scale of land surface variables, The first factor would be whether the initial land surface would have any anomaly, because they just inherently, they have this inherent memory that can persist on subseasonal-to-seasonal timescale. So they can serve as important source of S2S drought predictability as indicated by past many research. And so their accuracy matters in forecast system matters. And also depend on forecast scale of meteorological forces. For example, if the dynamic model forecast just provide an incorrect forecast of precipitation anomaly or temperature anomaly, then there's not much chance or hope for us to produce a skillful forecast for soil moisture tendency, the soil moisture change with time. And also depend on the performance of the land surface models, which essentially serve as a tool that translate the effect of the meteorological anomalies into the changes in land surface state. And additionally, even though not listed here, in couple framework, the coupling between land and atmosphere also matters. So next, just really quickly talking about this importance of this accuracy of land initial conditions, which probably not new to some of you. Just want to quickly point out that this accurate soil moisture initialization is important for the skillful week 3 and 4 forecast for precipitation and temperature for drought associated with drought. Here, just based on 4 sub-X models and the 3 drought events, and you can see that the larger bias we have for the soil moisture initial condition, the larger bias we tend to have for precipitation and temperature forecast. And more importantly, the accuracy of land initial condition would matter for the forecast of land surface state. And here, just use the GEFS-12 as one example. So this is some work we did at CBC. We incorporate GEFS-12 in our subseasonal drought forecasting. And when we incorporate that, we will do some research, for example, assess the accuracy of the reforecast initialization, which shows relatively low accuracy in the western interior US and also at the deep soil layer. And this just pretty well reflected in the forecast, in the scale of the forecast. So at CBC, just in order to overcome this challenge, we would produce this outline NOAA land surface forecast using the NOAA land surface model from EMC, and so that we can have this initialization using the NOAA land analysis we produce at CBC by driving the NOAA land surface model offline with the assumed meteorological forcing with adequate land surface spin up. And you can see that just substantially improved the forecast. And third challenge will be related to the availability of the forecast model output. I just mentioned, we do need the variable for generating the drought indices, especially those from the land surface output, model output, but not all models would provide this data. So as CBC, in order to overcome this challenge, we would just produce a land surface forecast just by driving land surface model offline with meteorological forcings from the dynamical model forecast. This way we can get the data we need. And also on top of that, we can have this added benefit of improving land surface forecast through the use of more accurate land initial conditions. We can use more skillful meteorological forecast to drive land surface model, and also can provide this flexibility for us to use more advanced land surface models. The first challenge will be related to decadal trends. I believe later in this workshop, I'm going to hear some presentation on this topic. So here, I'm just going to be really quick here. Just want to quickly point out that the current forecast system are known to be problematic in simulating observed trends, especially in surface air temperature, and that can adversely impact drought prediction, especially for the drought indices and types that are sensitive to the changing climate, such as snow drought. And the fifth challenge will be related to the handcast period. In the current forecast systems, the handcast period is primarily for the current climate, and the length typically range from 20 years to about 40 years. So they're appropriate for producing forecast anomalies relative to the current climate. But think about the drought, which not only include short-term drought, but also long-term drought. So they may not be adequately long to capture the effect of the climate variations on the longer time scale on drought. Here, just really quickly, if we just use the current climate and build this objective drought monitor, compared to USDM, US Drought Monitor, which currently is considered as a golden standard for drought monitoring, we're not going to be able to produce much long-term drought in the southwestern US as USDM. Only when we use a much longer base period can we produce that. And the sixth one is related to objective drought blends, as I just mentioned, SVC. when we produce all the drought forecast, we need to produce a forecast for different drought indices, different time scales, and also different lead time. And then we need to integrate them all together because not all users would have this drought background. So we need to develop and also apply updated drought plans to take into consideration of their respective physical characteristics of these drought indices and different time scales, and also need to take into consideration their forecast skill so that when we integrate them all together, the integrated drought condition can be skillful. And lastly, is related to the service side. For the product visualization, we need to incorporate social science. This really need to make direct connection with the end user, show them, the draft of our product, and check on their understandability and their interpretation. Just to make sure they have the correct understanding, so that can incorporate that in the decision-making process. And also the product application just need to involve this active engagement with the regional and sector user to understand their specific needs. All right. So here just to summarize, this is just the same as what I showed at the beginning of the presentation. And here just want to quickly point out that drought forecast is a downstream product of TNT, of meteorological forecast and land surface forecast. So really, what we can get, the skill performance of the product we can get to a large extent depend on the skill performance of what can be made available to us as an input. So in the interest of the time, I'm just going to leave this last slide here. We do understand that addressing some of the needs can be a daunting task for, in particular, improving skill for precipitation can take years or even longer to achieve. But just want to point out that any improvement in this aspect can subsequently lead to improvement in drought forecast. Thank you.
Thank you very much for that talk. Moving right along, Logan Dawson. Finally figuring out.
Thank you. All right, good morning, everyone. My name is Logan Dawson. I'm a Science and Operations Officer at the Ocean Prediction Center. I'm here to talk a little bit about our forecaster priorities and needs as we move into for S2S modeling, as we look to extend our forecasting capability into the subseasonal, especially in seasonal timeframes. First, I want to acknowledge multiple colleagues at OPC that provided some excellent input for this presentation. So just a bit of a background on who we are and what we do, in case you aren't familiar with the Ocean Prediction Center or the U.S. National Ice Center. So OPC is one of the 9 NCEP centers. We're located here in the building, along with a number of our other sister centers. Our mission is to provide maritime safety information in the form of marine wind and wave forecasts and warnings, primarily for the extratropics and the North Pacific and North Atlantic basins. Our mission overall is to protect life and property at sea and also livelihood. So livelihoods there hints at the economy, so enhancing maritime weather readiness and the viability of the maritime economy. You can see there in the image in the lower left, that's the National Weather Service Marine Forecast Responsibility Area. OPC focuses on the extratropics and that purple outlined area. So large portions of the North Atlantic and North Pacific. That's on our ocean forecast side. On our ice services side of OPC, that branch is also part of the U.S. National Ice Center, which is a tri-agency effort between NOAA, which OPC is a primary contributor now, and then U.S. Navy, and the U.S. Coast Guard. So the U.S. National Ice Center, they provide global and tactical scale snow and ice products, including ice forecasts and information for decision support services for especially vessels like Coast Guard cutters moving through the Arctic or the Great Lakes, for example. So just a couple examples of what we do on the ocean forecast side, marine winds and waves. We provide forecast information right now, primarily in the let's say the medium range time frame, so out five to 7 days in advance. This is in the form of graphical and text forecasts describing weather conditions that might present hazards to the mariner. So surface forecasts, 500 millibar charts, wind and wave forecasts. So that type of information, examples there of some of our text forecast products for the Atlantic, and as well kind of the backbone of our product or our product suite is our surface analysis that we produce in collaboration with some of our other NCEP Center colleagues. On the ice services side, again, this portion of our products and services happens out of the U.S. National Ice Center down in Suitland, Maryland. So they provide daily ice analyses of sea ice extent. There are two examples on the left side, the extent of the marginal ice zone with concentrations in the 10 to I think it's 1 to 10% and then 10 to 80% sea ice concentration for both the Arctic and Antarctic. This information is also provided for the Great Lakes. Included in there is information on ice concentration and ice thickness. And then on the decision support side, they provide detailed information for Coast Guard cutters, research vessels that might be leading convoys of ships through the Great Lakes, through areas of the Arctic. Focus here just on OPC since that, or sorry, USNIC, since that's part of OPC, but there's also the Alaska Sea Ice Program that provides similar decision support for Alaska region, and they share relevant needs when it comes to predicting sea ice. So just a little bit about our extreme weather, the expanse of it, how serious it can get. So on average, across our areas of responsibility, we deal with around 100 hurricanes, tropical origin, and extratropical storms that produce hurricane force winds within our domain annually between the two basins. So a lot of extreme weather. Summer might be a little bit of a quieter time for us unless we get recurving tropical cyclones. But then our mid-latitude winters are very, very busy with vast ocean areas, the impact of the Gulf Stream in the Atlantic and the Kuroshio Current in the Pacific. We deal with extratropical explosive cyclogenesis, and then as well on the ice side, again, hazards as in formation of sea ice, and then in particular heavy freezing spray that we also deal with. So shifting towards S2S timescales, want to talk about where the relevance of marine and ice prediction is for these timescales. So starting with ship routing, and in particular polar routing, S2S prediction of ice, winds, and waves can have important applications for transoceanic shipping across our large areas of responsibility. Those transits take upwards of a week, or if you're doing loops, multiple weeks. And then polar routing and cryospheric research as well. Got an image there of some of the Arctic shipping routes. As sea ice, as these channels begin to open up more and more with lower sea ice extent in late summer, early fall, these channels are open longer. So there's actually a benefit of using these routes just because they can shorten transit time. So the ability to predict the opening and closing of these routes through the Arctic, and then also the Great Lakes to freeze up and melt has great importance. So an example here of some of the current operational products provided out of the USNIC for 45-day outlook for sea ice concentration and thickness. You can see here, this is a week 2 outlook, and then they're going out to week 6 information. Currently, these outlooks are based primarily on information from the Navy ESPC ensemble mean. That's a 16-member ensemble that does have full atmosphere-ocean ice coupling. So we're really looking forward to the coupled applications to come from NOAA to really enhance the information that we can provide here. And then just an example there of also being communicated in these graphics is information on model confidence, or i.e. Ensemble spread, just to describe the variability in the forecast guidance, and then just reiterating there. I'm sure these products and services would be greatly improved or greatly benefit from the coming additional guidance from UFS applications. A little bit more on the marine side. So again, I mentioned the number of hurricane force events that we deal with on an annual basis. There's just an image of one season, 2022 to 2023, across the Pacific. You can see that our in the Pacific, our kind of high point for these extreme wind events is on the western side of the basin. Again, the impact of that ocean current. The image on the right there are sea surface temperature anomalies from calendar year 2022. So there's certainly an impact. We're seeing that there's an impact from SST anomalies in influencing the intensification of these storms. So this is something that we want to be looking at more, and something that coupled model applications can certainly help us with predicting more or busier periods of activity further in advance. So kind of moving into that subseasonal space, we had recently, in collaboration with EMC and AOML, we've had an experimental product developed that provides week 2 forecasts for winds and waves hazards. So probabilistic forecasts of gale, storm, and hurricane force winds, as well as seas or significant wave height greater than some critical thresholds. So right now we're just using this product internally, and our forecasters refer to it. But I think our customer base is really interested in seeing more information like this. And again, couple model applications will certainly help improve the quality of this type of a product, and being able to simulate the interactions between the atmosphere, ocean, waves, ice, and so on. And then not exactly S2S timeframes, but since we're here talking about, say, the Global Ensemble Forecast System, I want to mention that we had a summer student this past year who worked with us on looking at evaluating probabilistic forecasts for winds and waves on weather timescales. So these are day 2 forecasts, composites of probabilities of winds exceeding gale force between forecast hours 24 and 48. We're looking at a few different ways of generating probabilities, things like neighborhood maximum ensemble probabilities, ensemble agreement scales, just showing those as examples, really looking at how can we better identify the extremes in these ensemble forecast systems. So just mentioning some of the shortcomings and challenges, and I'll go through these quickly, and happy to talk with people later today or tomorrow if you have questions. So, currently GEFS is not fully coupled, and so therefore relevant interactions, atmosphere, ocean, wave current, so on, aren't simulated. And as I mentioned, the air-sea interactions, certainly play a significant role in intensification of the extratropical cyclones that we deal with. On the wave side, the high-end values that we see, extreme wave heights are often underpredicted in the GEFS system. So a question there of, is additional resolution needed, spatial that is, or can we explore AI/ML as a means to provide cheaper alternatives to predicting not only the extremes of these waves, but the full wave spectrum in terms of different wave systems. And then I mentioned having the probability products available directly in the output greatly speeds up the ability of OPC to get our get this guidance in front of our forecasters. So just closing with some general forecaster priorities. Mentioning here, I know that GEFS and SFS, the next versions are coming as coupled systems. We're really looking forward to seeing that. Having reef forecasts available to provide the model climatologies to better highlight those extremes, facilitate bias correction, train AI models to identify hazards. That would be greatly beneficial. Expanded utilization of methods like the neighborhood max ensemble agreement scales for identifying the extremes. There's an increasing need from our customer base for more detailed, skillful guidance on individual wave systems, identifying not just the significant wave height of the combined seas, but different swell systems. And then gridded data for ensemble members and the ensemble mean. This in particular on the side of ice prediction will be of great importance. And then I won't read through this slide in detail, but I made an effort to identify some of the specific product needs that we have for GEFS and SFS in terms of reliable probabilistic guidance for some of our different hazard thresholds, just to make sure that that those are identified. I mentioned in terms of probabilistic information, I think for the GEFS system running out to 16 days, the weather time frame of the GEFS, having daily probabilities, and then for the subseasonal run, having weekly type probabilities would be beneficial. And then I think weekly and monthly probabilities would be really of great interest from SFS. In the interest of time, I'll stop there. Greatly appreciate the opportunity and looking forward to learning more here this week with all of you. Thank you.
Howard, thanks so much. Great talk. Our final speaker for this session is Mr. Howard Townsend.
All right, thanks very much for the invitation to be here today. Just want to do a quick check. How many people from fisheries are here in the audience? Raise your hand. Okay, how many people here have worked with somebody from NOAA Fisheries? Okay, good, that's exciting to see. How many folks here are familiar with the CEPI? Okay, good. So I'll be presenting some new information. First off, I should acknowledge my co-author, Roger Griffiths, who's heading up the CEPI project. And a lot of other folks. We're just the two who put the slides together. There's a lot of folks from around the country who've been involved with this. So the reason we got started with this CEPI was that we are facing a lot of major challenges: droughts, warming oceans, loss of sea ice, rising seas, ocean acidification, et cetera, that are influencing marine ecosystems and fisheries. And we get an increased number of extreme events, and also longer term change that we have to deal with fisheries. And also not just the ocean, the Great Lakes. So, fisheries is kind of the spearheading this operations, but we're also working a lot with OAR and Ocean Service, so I should acknowledge that as well. So, first, just to talk about a little bit of what we do in NOAA Fisheries, we have 450 fish species that we have to provide scientific information for to help with management. We've got probably 200 endangered species, marine mammals, sea turtles, those sorts of things that we have to provide information for. I don't know how many aquaculture decisions and siting decisions we have to make, provide information for, and just general information on habitat and the National Environmental Protection Act to provide information on how ocean actions might affect important habitats. And finally, how will the fisheries community, so we have a big socioeconomic component to this, how will the communities prepare for changes in how fisheries and living marine resources generally will respond to the climate. And we need information across a range of timescales from sort of the seasonal, subseasonal, where this is kind of a new area we've been working in for the past 10 years or so to really provide advice in real time to folks who are out in boats and going fishing as far as, when to avoid marine mammals or endangered species while they're fishing. We also have kind of annual cycle for stock assessments where we predominantly used sort of population dynamics models separate from anything going on in the ocean. We're starting to realize more and more we need to incorporate ocean and climate information into those. And we have been doing that to some extent. And then broader, just, strategic thinking about when species shift distributions, how do we, influence our management structures, our governance structures on how to best deal with these changing distributions and resources. All right. Let's not go in here. Oops, so it would little lag there. Sorry. Okay. So, like I said, these are the sorts of decisions we make, and we have been incorporating climate ocean information in sort of not an operational way, not in a regular delivery sort of way, sort of as needed basis around our regional science centers and with our regional management offices, and with little eye towards sort of long-term planning. We sort of have these annual decision-making processes or sometimes shorter decision-making processes that we deal with. And with the CE5, we're hoping to build in a system that will allow us to regularly deliver ocean product information that can be pulled into some of our fisheries models, and make sure that's operational. And we're making full use of climate and ocean information, in hopes that this will help to improve our decision-making processes and planning for these longer-term changes. Like I said before, this SEFI is a long-term, not a long-term, it's a three-year initiative. It's a cross-NOAA effort, primarily spearheaded by fisheries, but with OAR and Ocean Service. We have been working in these, in various regions and various aspects of this, working with pulling ocean models into some of our fisheries and living marine resource models. We really are thinking about the whole end-to-end delivery of the information and making this sort of operational and enterprise-wide. So the process that we're building here is we're working with OAR, who's working, develop MOM6 models to generate some of the ocean modeling products we would need, deliver those through a portal that then largely fisheries modelers will be using for management strategy evaluation, incorporating into stock assessments, just looking at spatial shifts in distribution of the fish species as they respond to various climate change and variables in the ocean. And finally, we're presenting new and different information and ways of thinking about managing species to our decision makers. So we really have to think a lot about what those products need to look like and work on that a good bit. But classically, we have had to make decisions and think about the ocean on a variety of time scales, from sort of these longer term decade sort of things, rebuilding plans. If a stock is overfished or overfishing is occurring, you have to plan for how to rebuild that stock by changing fishing, by taking into account how climate might influence the ability for that population to grow back. And just generally, how does the industry capitalize, what do they invest in their, for fishing gear and boats and that sort of thing in the long term as species shift distributions. Classically, a lot of our information has been focused, or mostly our information and modeling has been focused sort of on these annual catch limits. How much can you catch of this tuna or species X, Y, or Z? And but we also do have area closures. If there's a reduction in the number of fish in an area, we have or overfishing in a short term, close areas, and just generally how can industry operate, as I said before, to avoid catching the things they don't want to catch and do catch the things they do want to catch. And so we do need a good bit of work in this seasonal to subseasonal range. And right now we were working with MOM6 to provide, we have MOM6 of these 3 major regions to provide a couple with biogeochemical models to provide the information we need for this is mostly applications on the shelf. That's most where our fishing effort is occurring, and our concerns with endangered species and marine mammals and sea turtles and that sort of thing happens. We've been working with OAR and other folks to figure out what's sort of the Goldilocks resolution. If it's too fine, it will take too long to run. If it's too coarse, we're going to miss some of the key environmental signals that are driving fish and living marine resource species. We've got sort of starting to build some seasonal and subseasonal forecast with OAR, ensemble projections to kind of figure out what's we'll just deal with uncertainty, I guess, in the seasonal subseasonal scale. But the decision support team, which is primarily the fishery folks, we're just now starting to bring people on board to help develop habitat and distribution maps and see how those change in response to climate change over time. And building ecosystem-wide forecast projections, doing these management strategy evaluations where we look at projected changes in an ecosystem model and simulate our management actions on that model to see, what under different scenarios, different climate scenarios, different fisheries management scenarios, how can we best capitalize and do, best capitalize on the stocks, and get good return on investment for the industry while also maintaining the sustainable fisheries and maintaining endangered species and other living marine resources. So can't provide a nice crisp list like Dawson did of exact things we need, but I think over the next 3 years, as we have a more close working relationships between our ocean modelers and our fisheries modelers, we're going to have a much better idea of what we need. And I think MOM6 will be sort of the lead model for now, but I think in the future, we're going to have to think about a range of other models as well. So realizing this lunch, I'll keep it short, and I'll just say, if you have any questions, we'll have a question session, or you can email me later. Thank you.
Howard, thank you so much. And yes, as Howard mentioned, we are right at lunch. I would like to leave the floor open for maybe just 1 or 2 questions here for a few minutes. If anyone has a question, they could come down real quick for any of our speakers. I see one.
Yes, it's a question, hydrology and drought. We have seen that for the drought applications, there is quite a lot of work on post-processing of the forecast and provision enforcement of the land model. And this forcing the use for hydrological modeling with harder spectrum, but it could be the down scaling, temporal and spatial down scaling. I think it's probably unrealistic to expect the output from large ensembles. for hydrology. So one may need to do some mistake.
Anyone want to comment or answer? I think everyone's. Oh,
Yeah, this is Royce. I didn't hear the question. It was too hard. Could someone summarize it?
go ahead.
No, I didn't hear the question. Could someone summarize it? Hydrology, and that's it.
She's coming back. Give us just a second. Oh, we got a different one.
Yeah, I'm just going to be really short. Yeah, I saw that. That's a good point. Currently at CBC, we have to do this post-processing separately, from the forecast data. But I do have one question for, all the developers, whether it is possible for you to generate your forecast first and then, find out the lines, and then when you produce your own forecast, whether it is possible to, you cover the post-processing. That can save some effort to, our product developers.
Let's do one or two more.
Right, this is a question mainly for Royce, who I think is still online.
Royce, I think you're there, aren't you?
I am here.
Okay, yeah, so recognizing that skill for forecasting seasonal precipitation in the exotropics is pretty low. We've been experimenting in Environment Canada with using daily outputs to instead predict a number of rainy days exceeding some threshold like a millimeter. And we found that actually tends to be more skillful than total precipitation in certain regions and seasons, such as Western North America in winter. Is there any demand for that type of information?
Could be. So here's one thing. This is where I'm gonna get a little into my other passion is drought. So I want to clarify a real quick comment. So I think Logan from OPC hit it really great. To run the models we need to use, it's not that we can't use a probabilistic ensemble. We need an actual grid that says at the 25th percentile, this is the value, at the 50th percentile, because we need those actual numbers in the model. For the days with precip over that, I think that can be useful, because one thing on the drought monitoring side we use a lot are the standardized precipitation or standardized precipitation evaporation index, SPI. And as we're looking for drought prediction, which is kind of that total water prediction, one thing those indices don't account for is the spatial distribution of that rainfall. So if I've got a 60-day period and the first 2 to 3 days of that period have a lot of that precipitation, well above normal for what my period is, I will show a high SPI number. Particularly, this is problematic in desert areas or western areas, but it doesn't really account for that. All that precipitation was front loaded in that time period, not. So I think some sort of output like that could actually be useful, because then if you're looking at the frequency of precipitation, how much how much is falling of that? I think that could be useful. That's something I don't think we really explored a lot. Is not just looking at the rates or whatever, but looking at the frequency of events. Because if you're all front loaded to that time period, while you're doing that calculation of I need 100 millimeters of precipitation to match ET, and you've matched it, but it's all on the front end. So I think that certainly could be useful. These are things that we're in the drought community certainly talking about in hydrology. So yeah, I definitely think it'd be useful.
Thanks, Royce. We've got one more left. Then I gotta let these folks eat.
So same question for Royce. Like I saw you are talking about the hydrologic forecasting. So did you utilize like 37,000 key stations for rivaliant plot? And if you did it, like did you calibrate the model using your national weather model, or like is there any other external model you use for the calibration? And what is the time range like for velocity? Is it like a 6 hour or like hourly? I'm just asking. So did you utilize that?
Yeah. So in the water model, there's a lot of references, and there's folks there and probably are in the room that if Brian Cosgrove is there, he can tell you all the details. We use a 40-year retrospective, and then we do calibrate 2 actual river gauges. I think that was what the question was. from what I could understand. Again, it's a little hard to hear with the echoes in there, but yeah, there's others that are much more. But yeah, we do use a 40, and actually believe one of my colleagues from OWP is going to talk about what we need for HEFs in that retrospective. So we do use a 40-year retrospective. I believe that's what the question is, and we do use available gauge data for calibration.
All right, let's hear one more round of applause for our speakers, please. We'll be having lunch till 1:30, and also please continue discussions here online in Slack. We'll also be having a second session on this tomorrow at 8:30 in the morning. So we'll see you all at 1:30. Thanks so much.